Say out. Ready?
You call it like.
We got 18. That's something you can see. We got 18. The only thing is because you know how long
Chris, want cigarettes? Oh, wait.
it looks like a square.
I don't know, my foot is killing me. Said you'd be mad. Hasn't hurt for 2 weeks.
Okay. Let's talk about this for the test. I'm going to give you guys some good sample ideas that you should definitely know. Stuff that we've talked about, obviously. Nothing on it will be new. Like, every time I make a test every year, guys, I look at the previous year's test, but then I change a lot of it. And I noticed that even last year, like I talked about things last year that I didn't talk about here. But then I talked about a lot of new stuff with you guys that I didn't talk about last year. And it's constantly changing. I'm adding stuff to your curriculum, I'm taking stuff out of theirs. And I'm just experimenting, seeing what works best and what actually is the stuff that you really need to know. All right, so first of all, just basic definition. What is a fluid? What is a fluid?
It's a state of matter.
A gas or a liquid, those are the states of matter, good. What properties do they have?
Takes solid.
It's malleable.
Yeah. It has the property of a solid.
Good. If it's, first of all, if it's a liquid, let's say if it's a liquid. If something is a liquid, it takes the shape of its container right away, right? It fills it up. And what does it have a definite amount of? Volume. Is the volume going to, guys, come on. Turn this way, focus. If you have a liquid, and I pour from one glass to the other, assuming nothing gets left behind in the glass, that's adhesion, that's different. So assuming we pour from one glass to the other and all the liquid goes over, it's the same volume, isn't it? The volume doesn't change. Now, so it takes the container shape and the volume doesn't change. It's a fluid. What about a gas, though? Think about a gas. You fill up a balloon. It takes the, God bless you. It takes the shape of the container, right?
Yeah.
But if I didn't have a container that enclosed it completely, what would happen to its volume?
Spread.
It would spread, right? Think about a gas. If you have a gas, or if you have like, ever see one of those like helium tanks or hydrogen tanks where they're actually like you hook them up to the balloon and you just turn the little knob, it fills up the balloon. Imagine though if you didn't have a balloon on the end of it and you just open the helium tank. What would happen to all the gas? It would just come out, right?
Actually, the tank would probably kill you.
And it would go from a tank. It would go from a tank volume maybe this big, and you release it for a little bit, and that helium starts to fill up the room. So its volume is not constrained. Its volume is not constrained unless it's what?
Contained.
Unless it's actually contained around all surfaces. Whereas a liquid, so think about it this way. Here's your liquid. It takes the shape of the container, even though it's open at the top, right? But if you pour, if you pour a gas in here, which you can do technically, you can pour gas. I know it sounds weird. But if you poured a gas in here, and there was all this gaseous matter, what would actually happen to it is it would start to eventually come out. Its volume is not consistent. So for a liquid, the volume is constant. Again, we're assuming no evaporation, all that other stuff. And of course that takes effect. But for a gas, what happens to the gas? Its volume is not constant. Its volume is only a function of its container. For example, what if I turn this container upside down?
What about it?
Then it is contained. Think about it this way. If I have helium, and we talked about helium, because helium is less dense than air, it floats, right? So if you took that container, like this, and you filled it from below with helium, it will try to rise up, won't it?
Yeah.
Because helium is less dense than air, so it'll actually be contained there. So the gas part is a little bit confusing. Whereas a liquid, the volume is always constant. Okay, it's always constant.
Okay.
All right.
The definition of a fluid is a gas or liquid, which
Types of fluids are gases and liquids. Fluids themselves are things that just flow, really. That's what you can think of, things that flow. But you should know your properties of fluids, okay? Just a general idea is what happens to a fluid over, as it goes from a liquid to a gas, what happens. A lot of that, guys, though, is just physical science. All right, let's discuss our three conditions. First, an object sinks. What can you tell me about that object relative to the fluid it's in? It's denser. Very good. Very good. So that's the second part I was going to ask. So first, this object sinks to the bottom. So this object's density, the density of the object is greater than the density of the fluid. That's our first thing. And I'm abbreviating. That's what you should be doing. Okay, the density of the object is bigger than the fluid. Now, there's a buoyant force acting upward. We don't know its value. Let's just say FB. It's got a weight acting down. Which of those is bigger? The weight. The weight is bigger than the buoyant force there. Okay, the weight is bigger than the buoyant force. That's when an object sinks. So if it's in motion, it's not suspended. It's actually sinking down right now.
Wait, save my life.
Okay. Next. If we think back to normal force, I'm standing here. Let's say hypothetically my weight in newtons, I have no idea what my weight in newtons is. Let's say it's 80 newtons. What's the normal force acting back up? 80 newtons, right? Can the normal force ever be bigger than me?
No.
Because isn't it just a reaction force?
Because then you will fly.
Right? Then I'd be floating. Very good. So can the buoyant force ever be bigger than your weight technically?
No.
Yeah, in water.
Be careful though.
No.
We talked about in class that when the buoyant force...
It's better floating.
Hand is up, thank you. If this object is floating, what's the actual buoyant force really equal to? We talked theoretically in class about this.
0?
It's really equal to its weight. The net is 0. The net is 0. So if the weight acts down, say the weight of this object is 80 newtons, if for it to float, the buoyant force has to be 80 newtons. And we talked about when they're equal, we said it could also be in limbo. Remember that? We said it could be suspended. Okay, that's another case of it. But for this object to really be floating, the buoyant force has got to be at least equal to the weight. Okay, it's got to be at least equal. We said, well, what if the buoyant force is more than it? Theoretically, it can't be more than it. Algebraically, we could solve it could become more than it. But realistically, it's never going to be. Okay, so if you find the buoyant force on an object and it turns out to be more, for example, if you find the buoyant force on this object when you're holding it down, right? If you find the buoyant force on it, the buoyant force might be like something like 300 newtons. But once it gets to the top, it's going to push with all those newtons, right? Causing it. If the buoyant force is 300 newtons, it's an imbalance of force. So the 300 newtons are acting up, so it's going to accelerate upward until it gets to the top. Once it gets to the top, it sits on the surface, right? So it's no longer a buoyant force of 300 newtons because I'm not pushing down on it. Now the buoyant force is just equal and opposite the weight. If they happen to be exactly equal and opposite, you might get something like we said in class, where it could be actually suspended. Okay?
Equal and opposite.
Again, this is the tough part. The weight of this object is 80 newtons. Let's imagine I push down with my hand. If I push down with my hand with a force of 100 newtons, now what force does it feel downward? No, I'm pushing 100 in.
Wait, how many did you say?
The weight is 80.
108.
I'm pushing down with 100. It feels like it's being pushed down with 180. Because this is really pushing down or pulling down, right? 80 newtons. If I push down with another 100, that's really me pushing down with 180. The buoyant force could be 180 back upward, which means it's just going to cause it to float to the top there. Even though I'm pushing, it's going to cause it to float back up. But once it gets to the top of the surface, it can't be more than the weight, or else it would continue to float. Right? Think about it logically. If the buoyant force were actually more than the weight, the object would just start to float, which is like air. It's like air or a hot air balloon. That's how a hot air balloon works there. So the idea that when they're actually equal, when they're exactly equal, when this happens when it's in water, then it means it's suspended here. Okay? For this to happen, for this to float up to the top, we know that the buoyant force has to overcome the weight. And once it gets to the top, they're equivalent to each other. So if you want to draw this one, so leave this one alone here, we can say that the buoyant force is equal to the weight, and it's suspended. For this one, we could draw it in 2 stages. We could say that first the object starts at the bottom, and the weight is acting down, and the buoyant force is acting up. And the buoyant force overcomes the weight. When the buoyant force overcomes the weight, it starts to come to float. Once it gets to the top, though, it can't continue to be more. It's going to be equal.
Really?
Again, the weight acts down with some value, 60. Or in this case, we said 80, but let's say 60 here. For this to cause it to move up, the buoyant force has to supersede it, or overcome the value of the weight. So it might be something like 62 or 63. But then once it gets to the top, it's going to just float, right? And when something is floating, it's like normal force now. Whenever it's floating, think of normal force. Think of normal force. Think of normal force, okay? Again, whenever it's floating, think of normal force. It's like it's sitting on a solid surface. So if I'm 80 newtons, the normal force is 80 newtons. So if it's floating, the buoyant force acting up is 80 newtons still. Okay? So this is like 2 stages. If you want to write stage 1, and we didn't go into a lot of detail in class, but I want to make sure that we're clear on this. We talked about it, but we didn't draw it as detailed. Sorry. Exactly. The buoyant force itself, well, one could be acting down, but the buoyant force itself is exceeding this value. So it's acting on the object. That's what the extra force is. It causes it to move up with acceleration. When there's a force, there's an acceleration, F equals ma, which causes this to float upward, When it gets to the top, though, it's no longer accelerating, right? It stops.
But we can solve.
So now it's a balance.
We can solve for the FB here, or solve for whatever.
Sure, so this FB could be like 100 star, and this could be 80, which causes it to float up, but then when it gets to the top, if it's still 180, it will continue to float, wouldn't it? But we can't have that, it's resting. So now, this becomes 80 when it's at the top of the surface. So this is like a two-stage process. You can calculate the buoyant force in the water, and if the buoyant force is bigger than the weight, it's going to float up. But what's the actual buoyant force on the surface? It's just equal and opposite. Kenny?
I was wondering for the other side where when the force buoyancy equals weight and it's like in water and it's floating in water.
It's a very weird situation because currents could push it down, currents could push it up, so we don't know. That's why I said it's in limbo.
Because because if you were to push it underwater, wouldn't it how does it?
If you were pushing down on an object, the sum of the weight plus your force of push would be equal and opposite the buoyant force if it was steady.
But then it wouldn't stay there, it would go up or down.
Well, it would stay there if your hand is there,
Yeah,
but then when you move your hand, the buoyant force is now much higher, isn't it?
Yeah.
And it's going to shoot it goes up. That's what this is happening here.
Yeah.
So I'm pushing down initially, which caused the buoyant force to push up with not just 80 newtons, but 100 newtons to counteract my 20 push also. Once I remove my 20 push, it floats up, and then it floats up, and when it gets to the top here, now the buoyant force is simply 80. Okay?
So the force, buoyant, and the weight are equal when it's on the top of the water?
Because it's like normal force. Yes.
And when it's suspended?
And I know in class we didn't go into much detail. We said when the buoyant force overcomes the weight, it floats up, we said, right? But we never talked about what happens at the top of the surface. So I wanted to verify, clarify
So
that.
if we have a problem, would it tell us whether or not?
Okay, let's do an example problem. Good idea. All right. So let's say we have a wooden block, and a wooden block with a density of 1, or let's say 0.5. 0.5. What's that? I'm going to do that eventually, but I'm just going to talk hypothetically first. Yeah. If we have a wooden block with a density of 0.5, and it's in water, what's it going to do? Float, or is it going to sink? Why? What's the density of water?
1.
Just a 1 there. And sorry,
Assuming,
yes. So since the density of wood is less than water, it'll float, right? So if you want to figure out what the buoyant force is for this object, since it's floating, you could just find the weight and set them equal to each other. So let's do an example now. Could you close it though? I appreciate that. I know it was open, you're right. It should have been closed, sorry.
I'm
trying to
keep
keep the
the
mind
wide
open.
open, but come on, you know. How long is it doing a lot?
I'm gonna live in a nice.
No, right?
I'll say I'm gonna put in standard units.
My dog will kill him.
Yeah.
Actually, let me put in non-standard units. So you guys have to convert. We'll go over that.
Does he make old people better?
I think I can.
Huh? You say what you just say that. I think Chihuahua will take down people.
I'll kick the mess out of Chihuahua. Get off my foot.
I send the message.
He just like Jordan Logan, man. That one movie with Jordan Logan. Like bad movie.
Trying to bite somebody.
Old movie. I don't like Chihuahuas at all. They look like bug-eyed, like.
Alright, so let's look at this problem here. Now, the first thing you want to think about, the wooden box has a certain density, okay, 0.5. Water, we said, is a density of 1, if we're in these units that we're in here. Okay, so it's in water. Did I put in water? Yeah, in water, thank you. So it's in water, so clearly it's going to float. So start with an image on the side if it helps you. Okay, start with an image on the side. It's going to float because it's less dense. Now, if it's floating, the weight acting down and the normal force, which is the buoyant force, are equal and opposite, aren't they? So for this kind of a problem, I want to find what really? The weight. But I don't have a mass, do I? Which is what caused a lot of trouble for students. But if you remember, rho equals mass over volume. Solve for mass up here. Solve for mass. Again, I want to know the weight. Weight equals mg. But I don't have the mass. So solve for the mass up top. Move the v over.
Equals rho times volume.
Very good. Take vp or v rho, sorry, v rho. Plug in it for mass. Now the question becomes this, and this is what confuses people. Which V, which rho are we talking about? What's actually going on here?
Volume density.
What's the volume in this problem?
V.
OVG.
The volume is 4
For what?
liters.
But what do I want in it? What are standard units? Meters cubed, very good. Meters cubed. So for this problem, to start, I got to convert this. Start, what was my conversion factor? Remember from liters to meters cubed? 0.001, very good. So here, if you have, and this is a conversion factor, 1 liter is equal to, this is a 1, 1 liter is equal to 0.001 meters cubed. You'd be given that if you have this problem. Again, any conversions that are needed will be given. So here, and you have it in your calculator also if you want to check. So if 1 liter is this much, then 4 liters will be 0.004. Okay, 0.004. So this we're going to start with 0.004 meters cubed. Now, I'm not looking at the water, right? I'm looking for the mass of the object, so I can find the weight of the object. So what is the rho that I'm going to use here? I'm not looking at the water. Remember, I'm looking at the object, guys, the object. You're using the 0.5. Again, we're saying that the buoyant force, hold on, Julian. We're saying that the buoyant force is equivalent to the weight. That's what we started with, because they're equal and opposite. The weight acts down, the buoyant force acts up, and it's floating. So we start by saying the buoyant force equals the weight. Well, the weight is mg. Well, mass is rho v. But what rho are we looking at? Well, I was looking at the mass of the object, the weight of the object, not water. So it's the density of the object. Okay, so that's where we're going to use the 0.5 there. But that's 0.5. No, how do I convert that one? It's in centimeters. I want it to be kilograms per meter cubed. Nobody's remembering this one. To convert this one, what is it? 1,000 is 2,000 factor. Okay, or 10 to the third. Very good back there.
He's definitely throwing out.
So instead of 0.5, what do I have?
500.
500. Alright,
I chose to put the wrong number.
this is where memories come in, people. We talked about this. To go from grams per cubic centimeter to kilograms per cubic meter, you multiply by 1,000. We derived that in like the second class of fluids when we talked about this. Okay? So if you're given, these are the only units you're going to be given for density ever. This is the most standard one you use in scientific applications. When you're actually doing any calculations, this is the one you're going to use. So if I went from here now back to here, what would it be? Divided by 1,000. Very good, Kenny. Again, inverse operations, right? Okay? So 1,000 times 0.5 gives me the 500 there. 1,000 by 0.5. And what's G?
9.8.
I'm not going to be okay.
Okay, and all my units are standard. If I actually do this, I'm going to get newtons as my answer. Take a look. Your meters cubed will cancel with your meters cubed. You have kilogram meters per second squared, which is a newton. Think about it this way. This is like mass. This is like mass with kilogram.
You guys.
That's acceleration. What do you get for an answer? Yes. Sorry, Julian, I missed your question.
I had 500 the whole time.
500 questions?
No, 500 answers.
For this number. Did you use the unit converter?
No, I just did. I remember the 1,000. So
Awesome. Anybody try the unit converter? You can do that. If you go to the unit converter and go to volume or go to density, you can convert any of that stuff. You could convert liters to meters cubed. You can convert grams per centimeter cubed to kilograms per meter cubed that are density. Just go to your unit converter and practice. Explore it, please.
You want the answer?
Yeah, what do you get?
0.6.
Okay? Which makes sense because this comes out to be 2. If you multiply these two, you get 2. 2 times 9.81 is 19.62. So the weight is 19.62. So what's the buoyant force? Same thing. Very good. Again, it's floating on the surface, so the weight acting down is equal and opposite to the normal force, which is really the buoyant force here.
And the buoyancy formula is volume, rho, gravity.
Yes, if an object is submerged, for a submerged object, it's rho VG. But it's the volume of the object, or the volume of the displaced water, the density of the water times G. Whereas this is the density of the object. But think about it, if you put a 1 in here for the water, it would be 1,000, right? Which would cause the buoyant force to be more than the water, or the weight. That's why it's floating, really.
So, Mr.
You
Howe,
plugged in the other one there.
when
Okay?
we say that W would equal, or what we have to say that it's force buoyant, buoyancy force has to equal buoyancy equation. Does it matter what you put? Just this one's gonna equal.
Well, at the end, you would, the answer is for buoyant force, so you would, yes, absolutely list it like this.
But like, when you get force taken off, you just leave it weight.
Well, here's what I would do. I would say FB equals W equals mg, and then I would actually just put FBs in here from now on. But I didn't want to confuse people. But I would put FB from there on.
Can we do one
Okay.
where water?
Yes.
Object in water.
Yes, absolutely. That's what Star asked about too. Objects submerged in water now, right?
Now we can look at the weights of
Matter of fact, let's do
Submerged in
gas.
something. Yes.
Make sure you get something
What is
that weight.
Yeah, that's why I'm asking.
So 740.
Try what everybody looking at all. Why don't you just look at
CM cubed or I. Depending on what you're looking at. I know. Guys, again, when in doubt, for units, use the converter for now, or just know what your standard units are. SI, you gotta know what those are. A kilogram, not gram, etc., etc. Alright, so, we've got an object chained underwater. It's chained underwater, sorry. Here's the surface of the water.
You're a cruel person.
It's not gonna work if it's not chained down, if something's holding it down. So, let's say, for this example, that the object in this case happens to be, it's got to float, and you want to use gas, which is 740. So let's say the object is again wood. We'll use wood again, and we'll say again it's, it's 500. So we'll say this is wooden. Depending on the type of wood, it'll change the density. Let's say for this case, so let's say the density.
Mr. Howe, you have to know the answer.
Oh, yeah. Density of the water or density of the object?
Well, the density on there is going to depend on what I choose as material and all that stuff. So. We're going to run out of time if I do that. We only have 20 minutes. I'm not going to go into the lab, but this is the exact answer.
Trying to get to a
Okay?
parent weight.
Use this method star, change your numbers, whatever they are in the lab, and then verify them. Okay? So here, we've got 500 kilograms per meter cubed as the density of wood. It's wooden. It's under, in this case, we're saying gas. We'll say this is some sort of gaseous state, which has a density of 740 kilograms per meter cubed. Okay, the density of the fluid is the density of the object. I should really specify, right? Now, if the density of the object is less, what's going to happen to it?
Go to rise.
It rises, but it's chained down. So when I release those chains, what's it going to do automatically? Float up, right? So right now it's submerged underwater. So it's going to have a buoyant force that is bigger than its weight. Again, because it's going to start to move up. So if I know the weight of the object and the buoyant force here, I can see what's going to actually happen. So for this kind of a problem, I want to find the buoyant force. For an object submerged, remember, it is what? Or does anybody remember this one?
The buoyant force is gas.
Well, what is the formula for the buoyant force when it's submerged?
Oh, rho.
Rho v g. So it's the density, okay? The density of the liquid or the fluid. That's the hard part here. Okay, the last example we did, we used the density of the object because we were finding its mass. Whenever it's a submerged object, it's the density of the displaced fluid.
So, but what I want to know for this one, for this example, will we use the density of the gas or the water?
Fluid, which is the fluid.
But both are fluids.
There's no water here, dude. This is gas. It's all gas.
Oh,
It's submerged under gas, guys.
Oh, see, where do I put the waves? There you are.
But the what?
The waves.
Because the gas, I mean, it can actually be contained in an actual container.
But that doesn't look like a top.
All right, so
Alright, now.
so it's a gas in a container. Sorry about that. All right, so whenever an object is submerged, when it's submerged, you're going to use the fluid for both of these. That's what you want to write down. Okay? On your test, you're going to see that exact formula like this. This is what you'll see. Rho F, VF, G. It's the exact formula. But you got to think back to the last example when it was floating. We used not Rho F and VF, we used Rho 0 or Rho object. and V object. Okay? The volume of the fluid displaced is the same as the volume of the object. So let's say the volume of the object in this case,
In this case, right?
it always is if it's submerged. Whenever it's submerged, it's the same.
That's what I'm saying.
Oh, sorry. So this case, yes, submerged. Say the volume of the object is,
It's 5 meters. Wait,
let's say it's 0.5 meters cubed, just to be simplistic here. Okay? So the volume of the object is 0.5 meters cubed. It's sitting under the water here. So I know the volume of the fluid that's displaced because it's the same as the volume of the object. I know the density of the fluid, it's 740. I know the actual gravitational constant. And what you're going to notice here is this. Plug in your numbers, 740, 0.5, 9.81, and solve for your FB. And what you're going to notice is that the FB is going to be more than the weight. It's going to be more than the weight, which means it wants to float. But once it gets up to the top, the FB will be the same as the weight. Okay, so here, for this kind of a problem, can somebody give me a quick number? Another person, do me a quick favor.
3629.7.
Thank you. Now do me a favor, instead of 740 here, use 500 to give us the weight of the object.
You changed it. It's less than 5.
What do you got?
2452.
2452.5?
No.
No, yes?
Wait, which one? Oh, yeah.
Good?
Why, hold on. I thought that,
Listen carefully. So,
oh, never mind.
the buoyant force acting on this object is submerged, thus we use the density of the fluid, the volume of the fluid. So we get the buoyant force. If you go back to the last example and you think back, how did we get the weight of the object? We did the density of the object times the volume of the object times the gravitational constant. So I asked Elizabeth to just make this a 500 so that I can use the density of the object. The volume of the object is the same, the gravitational constant is the same. So this is the weight of the object, this is the buoyant force. Since the buoyant force, when it's being held down, is more than it, once it's released, it will rise to the surface. So this is the buoyant force being submerged right now. But when it gets to the top of the surface and it settles out, what's the buoyant force then going to be?
2452.
Equal and opposite of the weight, because it's now acting like a normal force. Okay? 2452.5. So the buoyant force can be bigger than the actual weight of the object, which means it's going to float. But once it gets to the top and it starts to float, then the buoyant force and the weight are equal and opposite of each other. Okay?
Mr. Alpha, what's it?
What's the what?
740. Wait, why did you put 700? What did you put in? 740 and then...
740 is the fluid.
The volume is down.
But it's the same. The volume of the fluid displaced is the same as the volume of the object, 0.5. They're both going to be 0.5.
And why how do you 740?
Because then you put in grams per cubic centimeter. I use it in standard units, still grams per cubic meter. All right, let's take a look at... Okay, apparent weight. So, you got an object, it's sunk to the bottom. It's clearly sunken. All right? Its weight is 50 newtons. The buoyant force, unfortunately, is only 20 newtons. Okay, the buoyant force is only 20 newtons. Because it wants to float. This object is being held down. Okay? So, the buoyant force is only 20 newtons. The object is 50 newtons. What's the difference between these two?
30.
So what's the apparent weight?
30.
30. You're done. Again, apparent weight, which is F net, is equal to, and I'm going to put it in the order I put it on the exam so you can see, Fg, which is the weight, minus Fb. Remember, guys, this is W. Don't let that confuse you. Okay, don't let that confuse
When
you.
you guys are going to be a jerk, you would ask us to find the gravity and...
Well, yeah, you might have to find the weight of the object.
Yeah.
You might have to find the buoyant
Yeah,
force,
like that.
and it might be able to solve for this example. So remember, the weight of the object is rho O VO G. The density, or the buoyant force, is rho F VF G. And a lot of you use this in your lab, which is fine.
Which actually be
Okay? Remember, guys, buoyant force from the last example is here. When you're looking at the weight of the object, you don't use the fluid anymore, but you use the object itself. I think, Maria, this is what you asked me, right? Yep. And notice here, what could be factored out? G, what else actually could be factored out? V actually could also, because it's fully submerged. So the volume of the object is the same as the volume of the fluid being displaced. It's like Archimedes' principle. When he got in the tub and the water level rose, right? the volume of his leg that was in the tub was the same amount of volume that the water level rose by. So realistically, you don't even need those subscripts right now because it's submerged. Because it's submerged. So you might want to write that, because it's submerged. So I would say GV rho naught minus rho F, or rho object, sorry. Well, not, but that's fine for now. Okay, so you could do that as well. You will be given, guys, you will be given this formula right here. Okay, that's the formula you're going to be given for apparent weight. It's not going to say apparent weight, it's going to say F net. Okay, it's going to say F net.
Get it?
My God.
Because what creates a buoyant force? The fluid, doesn't it? What creates the buoyant force pushing up? Isn't it the fluid?
I would think the opposite. The air is doing it. The air.
Technically, yeah, there's a buoyant force on the other. Right now, it's a solid surface. So this is feeling like the normal force. You could think of this as the normal force pushing back up with 20 newtons, but what's providing that normal force is really the actual buoyant force. It's kind of weird stuff, I know.
I would think that the normal
The difference between these is 30. That's your apparent weight. So the normal force would just be 30 in that case. Okay?
we don't gotta worry about all that extra stuff in the formula. You just subtract the buoyant.
Yeah, but I'm telling you now, Star, if you're given an object and you're not given these two, if you're given the density of each and the volume, you need to use those. Okay? All right, let's say we've got an object, and let's say it's a box on the ground. So we're given the dimensions of the box. Let's say we're given the mass of the box, or let's say we're given the weight of the box. We'll say it's 200 newtons. I want to know how much pressure is being applied to the surface that it's sitting on. What's my formula for pressure?
P or rho E over M.
That's density I'm thinking of. Density you're doing. Pressure is capital P.
Oh, capital P equals M.
Rho MV?
No, it's
V
A.
over.
It's over V, man. It's over A, it's over A.
I don't know where I'm at.
So the pressure is always the force over the area. Well, let's think about this for a second. No, there's no person sitting on the box, right? So the force is just 200 newtons, the weight. That's all the force is. What's the area of contact of the surface?
6.
6.
No, it's just 6. Surface, not volume. That's the key there, okay? Be careful. Again, what is the area of this surface that's on the ground? It's just 6. Okay, it's just 6. So 200 newtons over 6 meters squared, because it's meters times meters. It's going to be 33 1/3. What's my units for this?
I'll tell you.
Who's the guy? Who's principal? Not our
KPS?
Pascal.
KPS or just PS?
Your units always are pascals. You might want to write them as kPAs when we're looking at atmospheric, which we'll do in a second.
So if we write pascals instead of kilopascals.
It's different. They're different things, yeah.
Right.
Whenever you get your answer, it's pascals. You can then move it if you like. If you want to write it as kilopascals, 1, 2, 3 spots, and kilograms. Either way is fine. But some problems are going to be atmospheric. Houston, I'm still answering your question. Some problems are going to be when the atmosphere, and it's given in kilopascals. So you need to have to use those actually.
Okay, but so if the problem is given in kilopascals.
You're going to have to use kilopascals.
I know, but like, so we would have to convert it back to pascals to do an answer.
No. All right. Before we get to more pressure stuff, guys, we have a lot to do. We have 10 minutes left. Let's go. Focus. I keep stopping here. First, fluid can flow in what ways? We're talking about 2 ways fluid can flow.
Back.
Vertically and.
Think about fluid in a pipe. If it flows smoothly, what kind of flow do we call that? Ooh, man, you guys got to look back at your notes. We had 2 terms. If it's flowing smoothly and steadily, we called it laminar. Okay, look back.
Whoa!
If it was not flowing that way, or if the airplane is shaking, if there's a what?
Turbulence.
Turbulence or turbulent flow.
How do you spell laminar?
Okay, we talked about this in class, guys. Look at fluid flow, and we looked at the pipe flow. It was when we did the cross-sectional area stuff.
You said it's luminance, it's
It's
laminar.
after apparently.
That's there, right?
Yes, after
Luminance.
I
apparently.
think it's laminar.
Is laminar, Ms. Howard?
Laminar. L-A-M-I-N-A-R.
She doesn't have them in her notes. There's something wrong there.
I'm 100% sure I taught about it. I know for a fact. So.
Can you say that again?
Laminar and turbulent flow. Laminar is smooth, turbulent is not smooth. There's a lot more to it than that, but I'm giving you guys a preview or summarized version.
Laminar is holding the pipe when it's
And that, you said it's an example beyond the.
Too many questions, guys. We're done with questions because we're out of time here. Stop with the questions, please. I don't usually do that, but we're all running out of time. This is stuff that's in your notes. Go look. You're asking me questions that you already know answers to. So, we talked about it. If you want to get through the review, we can. I can stop, though, and answer these questions, and we're going to miss the second half. I mean, there's still a lot to do here. The absolute pressure we talked about. We talked about absolute pressure being the idea where you feel the pressure on you from the atmosphere, but then if you're underwater, you also have the pressure of the water acting on you. So we talked about this being the atmospheric pressure. You'll be given this formula, plus rho GH, where H is the depth. Okay, where H is the depth. So in this kind of a problem, if you want to know the absolute pressure on an object submerged underwater, you need to know atmospheric pressure, which will be given. Atmospheric pressure is 101.3 kPa. That'll be given on the test. It'll be given in the problem if you need it. Now, rho GH. What was the rho we were talking about? What's on top of us if we're underneath the water? Again, the water. This atmospheric pressure comes from the air acting on you, but we're really underwater now. So underwater, there's 1,000. I know, but the density of the water with the air is 1,000. G is 9.81, and H is just the depth, whatever it turns out to be.
We always use fresh water, right?
Yes, we're using fresh water. Now, remember in class what I had you guys do? I gave you the total or absolute pressure, and you were given everything else, and I said find the depth. So keep that in mind. We did an example of that. Look back at your example. You might want an example where you have to find the actual depth. Okay, I'm going to stop at that one there. Okay, next. I want to get to the actual numerical examples, because those are the ones that cause trouble.
Remember you put it into a plastic thing.
Okay, theoretically, we have two principles from Bernoulli. Yes, two principles from Bernoulli. The first one was, what happens when I put my thumb over the end of the hose? The water goes faster. So as I lower the area, the velocity increases. That was my first principle. The second principle was the one that was misleading. If I lower the area, or in this case, if I increase velocity, I'm actually lowering the pressure. Remember that one, that's the other one. Those are the two principles we have to know. Again, if you increase the area, the volume will decrease. Or if you decrease the area, not volume, what is it?
Pressure.
Velocity. The velocity will increase. That was the first one.
I know.
I know, it looks like a V still. There's a lowercase v, guys, for velocity. Here, just to make it clear. If I increase the velocity, though, it decreases the pressure, which is what people don't think about. They think about when you put your thumb over the hose, the pressure is building up. But it's not actually. The pressure is building up behind it, but then the pressure at the nozzle is less, causing it to accelerate or speed up. Okay, so this is the key part here. If I lower the velocity, the pressure actually goes up at the end of the nozzle. Okay, this has to do with pipes and pipe cross sections. So for an example, if you're given an example as a diagram like this, and I say that this is, what's the word, by the way? I don't know if we talked about this in class, but what's the word when a cross section gets less and less?
We did talk about it.
What is it? Tapered. So I did mention it at least. Okay. So the word is tapered. Okay, I might use that word, so just so you know that. So for example, what would be an example of something that is tapered?
A water bottle.
A water bottle, very good. So imagine a water bottle with the tip at the end, and you squirt it. Isn't that tapered, really? Okay. What about like firemen? Ever see a fire hose? A fire hose is a huge taper on the end of it. The hose diameter is like this, and then it tapers off into a spout because it wants to shoot with high velocity. And there's an adjustable on there. It'll change the cross-sectional area to increase the velocity, get to the higher level floors. That's how a fire hose works. So why would a tapered thing be useful? Because it increased the velocity at the spout. Let's see. What if an object sunk forever? What would happen to it eventually? If it's sunk and it kept sinking and sinking and sinking, Okay, but if it's an object like, I don't know, what if I take
Eventually it'll flow back up.
my water bottle? Theoretically, let's say it's sunk to the bottom of the ocean. What would happen to it? Why would it crush? Too much pressure, right? Too much pressure? Okay. Bernoulli's principle, AV equals AV. This is the one with the cross-section and the velocity. If you have the inlet and the outlet. Inlet and outlet. Let me see if I wrote the formula with inlet and outlet, or if I wrote 1 and 2. No, I wrote 1 and 2. Perfect. So we're going to do the hydraulic pressure also. We're getting there, I know. So here, if you have a cross-sectional area in the beginning, so say it's a pipe and it looks like this again, and then there's a sudden change in the cross-sectional area, we can find the change in velocity. So if I know this area here, and I know this area, and let's say I know this velocity, I can find V2. What if these happen to be circular cross-sections? What's the area of a circle? So instead of these, you would actually make this formula, pi r squared V1 equal pi r squared V2. What would happen to the pi's? So really, if you have a circular cross-section, that's the formula it becomes. Okay, just keep that in mind. If it's a rectangular cross-section, what would the area of a rectangle be? L times width, or base times height. Okay, so in that case, we would use LWV, L and V is velocity still, LWV, this is 2, 2, 2, 1, 1, 1. That would be a rectangular. So imagine the air ducts above us. They're rectangular, and then they suddenly get to be a smaller cross-section. You would use the area, whatever this area is then, because it's a rectangle. Okay? What is V? V is velocity. V is velocity here. So you would have to given the velocity here, and maybe find the velocity over here. Or maybe you're given both velocities, and you have to solve for one of the radiuses, or one of the radii. So you have to think of a square root there. Don't forget that. So if you're given this velocity, and you're given the outlet radius, you can find the inlet radius by solving. You can solve for any of them. Just manipulate. Hydraulic press. We talked about F1 over A1 equals F2 over A2. This is one of the formulas. Okay, this is a formula that is not given. Okay, the reason I didn't give you this one is here's the reason why. It comes from Pascal's principle. And if you remember the shape of it, okay, if you have this fluid in this chamber here, and you have this fluid, the fluid pressure is the same throughout. That was the egg example you did at home. Why, when you crushed the egg, it didn't explode, because the pressure was equal out throughout the whole thing. So if the pressure acting here, the pressure acting on these surfaces are identical, the pressure in this one is the force over its area. That's what pressure is. Because you're given this form in the test, pressure equals force over area. Well, the pressure over here is also force over area. But what happens if the areas are different now, right? And the forces are different. I call that A1, I can call that A2. Now, using a formula like this, I can solve. So if I'm told that the area of my piston that I'm pushing down on, they didn't even call it a piston. Oh, it is called a piston later on. So if the area of the piston that I'm pushing down on is given, that's given as A1. And if I'm given the force pushing down, that's given as F1. Now maybe I'm saying, you know, the area of the cross-section over here is some other given value. I can find the force needed to lift the actual car. Or if I give the force needed, I can find the area needed to put the car on. So again, these formulas are just manipulative. You have to move them around to solve. Look at your example we did in class. That'll be more than sufficient to look at. I'm standing on 1 foot. I apply a certain amount of pressure, correct? Say the pressure is 10. Now how much pressure am I applying? On each foot, right? Isn't it 5 on each now? Why? What happened to my area? My area doubled, theoretically, because the shoes are identical, right? So my pressure was 10, and now my pressure is 5. So what about a car? How many spots are there going to be that contacts the ground? 4. Keep that in mind. Everything else we did. We're good to go. Perfect. That was perfect time as well. Yes. Hurry. I know it's a song, but... That's how it's supposed to be. I'll be down there for sure. It's about physics, right? Oh, sure. You're welcome, sir.
It's not good. Oh, he knows.
Again, guys, don't forget, if your lab hasn't gotten into me yet, please Thursday, please Thursday. If you turn in today, at the end of the day,
Yeah.
it's still gonna be late.
But I mean, as long as we get correct.
What about me?
Sometimes you can't rely on their partners, huh?
That's that?
All this weekend, he was like, I emailed this, I emailed this.
Why doesn't he copy you in the email for proof? That's what you say next time. You know what? You emailed him? Sure, copy me in the email. Because I never got an email. You know that I wouldn't lie to you guys.
I did get that email when you replied. He did CC me. Or I don't know if it was you or him. But the one that you said.
But
hey,
he originally said he
received.
sent one also, and I never got that, and
I
you
know.
never got that.
I think, yeah, I know. Yeah, I don't think that's right.
Mr. Howard, you still got parties?
They still out partying?
Yeah. I'm not talking about, dinner parties where they serve hors d'oeuvres and stuff. I'm talking about parties. Are you still gonna party with your friends?
Absolutely.
Yeah. If you
Is that not definite enough of an answer? Alright, we're gonna pick up from where we left off last class, guys. So have those notes out on area between curves.
Mr. Howard,
If you tried the homework already, please take a look at it, or please have it out. We're gonna look at some of those examples first. Houston,
can I use the computer?
can you what?
Use the computer?
You gonna watch the class?
Yeah.
Yep. You got headphones?
Yeah.
Shoot on over there, it's right next to you.
I got like 4 classes.
Thanks, everybody. Jasmine's what? Oh, jeez. She right?
Oh, no.
Oh, jeez. Oh, no. Use the new volume a second ago. Use the area. Technically, yes, it's similar, yeah. It's like your. The question was like, how would you pick it? A lot of them have pieces, you have to do them in pieces, so like different intervals. So you're thinking about the area you see in the graph and the bottom. So you take about that functions, either the top and the bottom, whatever it turns out to be, and you integrate it. The hard part is you're integrating around the y-axis. So you have to use pi, change the limits around. We're going to probably look at it today after school. We might still be doing this after school today, but we'll definitely look at that Thursday. Why don't you watch like an introductory video on it, maybe on Khan Academy. Look at like the volume of solids revolving around axis. And then sometimes they're called shell method or washer method. This method is another one. So they have different names depending on the authors. Who the author. But generally speaking, yeah, you're taking the actual function, you're integrating around the y-axis, which means you have to change your limitations up and go pi. It's a little bit funky. Alrighty, so your, oops, these are not your report cards at all. Alright, I put that note online, guys, on your report cards. Some of them had mistakes in them, and I submitted them, and they never got changed. So let's hope. Alright. So first thing, guys, I don't ever put comments on your report card, so if you saw a comment on the report card and it didn't make sense, it shouldn't have been there anyway. And I noticed that happening in other classes. Some of your third quarter grades might have been wrong. I don't know. I put the corrections in, but I'm not sure if they were or not. But these are definitely your correct ones.
Kenneth went to the bathroom.
Christian.
I mean, I don't know for definite, but I remember.
So I'm just concerned about your calculus grade right now. This is your whole report card here for you to look at. You're welcome to look at it. Houston. So again, just make sure your calculus grade looks correct. And I already put the third quarter grades up on Edline again. You can check there also. Kerry? Kimberly? Karen? So again, just make sure your calculus grade is right and there's no comments there. So if you see a comment on your calculus thing that says like may fail for the year, I did not. Okay? Nobody here is on the pace to fail for the year. So he was literally putting random comments on there. And then when Miss O'Connor sent me all this stuff on Saturday afternoon, I was like, oh my gosh, where are all these comments coming from? So then they already got sent out. I don't know what it is. There's something wrong with my program on my computer or the grading program.
It's like cooperative.
Yeah, it's like cooperative online.
Oh, well, that's fine. It says cooperative, sure. You might have picked, I don't know, I know, it just picked random ones for everybody. Something about one, something about others.
I've been getting comments from you all year, we're bad.
You've never got comments. Look at your other ones. It says like
I
sometimes
got
it works.
shows.
No way. I never got comments. Tell me, so.
I got shows on
Needs improvements.
Yeah, I got that.
That's definitely true.
Lisa's still wrong though.
Like you kids fall on
Guys, what is your grade based on a college prep? Seriously.
She
Based on work, actually.
She
One
gets-
person.
She gets a very small project like every once in a while, and if you don't do it, like you're screwed.
So it's pretty much just all science.
Yeah.
And if you do it, you pretty much get credit for it.
Yeah, you
Yeah.
either get an A+ or not. It's like that.
Yeah.
I was wondering that because I'm looking at report
We gotta
cards
get
and I see
B.
A minus, A, and then F.
I had an
How do
argument.
you go from A to F? For college, pretty much you do it or you
Because
don't.
you don't
kind
do
of
your
thing.
No,
hey, that's correct. Listen out. Listen out. That's the bad. I got C+. I'm C+.
Oh, so maybe you didn't have this, so that's.
No, I did messed up. I did,
You
man.
if you turn it
She's
in
the
like,
reason I'm not upset. She got the nerve to put a plus. Just give me a C.
Instead of sitting here and accusing and saying she, you should go after school and say, let me see my grade, let me see how it works.
Mr. Howard, don't let me say
What are you using?
2012, and then transfer to 2012.
No, that's not what I have. In gym.
I know.
No, but I mean, like, do you,
I have an A minus geography.
well, Mom, I had an A throughout the whole year, and then just go to the gym and my homework. And I was like, I don't care.
I'm in the
I'm over here.
I don't know how I'm passing it.
See?
I don't give you.
You didn't have a transfer.
I don't know, that's why I wanna know. I think it's a. Really much classes they do.
I don't know why you have it. Alright, I'll come to know. Christian, please. Hold on one second. Joe. Oh, wait, no,
I hate our health class.
You give us A.
So how do you
I had an A plus and a how
It's a free A. It's like, it's a free A.
I had an A minus.
Ours is a free A. That A, that art, that A plus an R got you.
Public speaking on a P.
Right.
haven't seen any more uses in my life.
I got
All the A's that they gave me
See, look, Karen.
My midterm
Huh?
exams didn't
They don't have
affect my grade.
Rosie, one sec, right? I want to see something next door. There's that too.
Christian, you got something cool? You got D plus and a C for good work. You know what I'm trying to make? I can do it, but yeah.
Go next door, use that computer. Yeah, that doesn't work without you, figure it out. Mr. Nolan's not here right now, so I can't do anything about that. Log in as a student user, plug in your headphones on and stuff. If something isn't working, come back and we'll figure it out. What's an I? Incomplete? Is that on your report card? For who? For what class?
PE.
It means incomplete.
How many concepts
Are you dressing every day? Are you doing all that kind of stuff?
We don't have to.
I don't dress every day either.
So you just ask. Go ask. Sure. You want to
How many sixes?
Okay, go play.
Have automatic in one girl.
It's hilarious. Tuesday and Thursday we reviewed the test. Don't watch that now. Watch that later. Watch Friday's class. Area between curves. Right?
I don't like him.
That was
Yeah, you hit.
What was area between curves? Yeah. We're gonna do today and after school both. So I think I might clear it up a little bit.
Are you going to the meeting? No, I usually just. Yeah, I know, but are you going after?
Who is it? Edgar only? Yeah.
Like, that's.
It's not that big of a deal because they already have all the documents that they need.
Alright, let's take a look at the homework real quick.
Hate
story.
That's the steps.
So many weird things there. Store one.
I
forgot the steps.
Like using the calculator.
Forgot like how to, what the command is or what stuff?
So I started.
Sure.
Thank you, I think we all deserve the same respect right now.
I don't know if it affects you as much though, you know what I mean?
Hey, you know,
Then I started drawing.
when you were trying to block me, so I was trying to find you for help, like my sister.
Alright, so next year I'm gonna be moving next year. I'm not gonna be in this area. That's what she's asking about. I told all the juniors yesterday because they would have me next year, and since you guys are graduating, I didn't think it would be as big deal for you to wait another day. I mean, I went into detail about why I'm moving with them and all this stuff because I knew some of them were really upset, and they were, which I understand because you know there's a lot of kids come here after school for help and stuff, and next year they all want to take physics, and there'll still be physics, but it's going to be somebody else teaching.
Wait, so you're not teaching?
I'm going to teach still. I'm definitely going to teach still, but I'm not going to be teaching here. I'm moving back to New York. That's where I'm from. I was from New York, guys. I lived in Philly to go to Villanova, then I moved down here. I've been here for 3 years.
Supposed to get paid.
The first year, no different. The first year I had you guys, it was when you were in 10th grade. That's when I was in the volunteer program. I'm not in the volunteer program anymore, okay? So I do get paid. It's not like I don't get paid.
I think you're paying here, you're still non-existent.
But you know what? The schools that I'm looking at are no different. I'm looking at Cristo Rey, New York, which is the Jesuit school in Harlem. It's in like in the Bronx, so up by like Central Park. And then there's another Cristo Rey school in Brooklyn, and I'm debating that one because I'm gonna. My grandma lived. Her house is in Brooklyn. She passed away 3 years ago or 2.5 years ago now. And her house has been uninhabited. So for the last 2.5 years, it's kind of been just collecting dust. So I'm gonna go there, live there, do a lot of work on the house. No, so my parents and my 3 different aunts own the house because it was my grandmother's name. It's a very expensive house, and it's a really nice part of Brooklyn. It's a house that has like 3 levels to it, and the 3rd level has always been rented for like the last 30 years to the same guy. So he's still gonna rent that, but now I have the 2 levels to figure out what I want to do with it.
And so yours,
I mean, it's not mine in possession, but I'm gonna pay them rent minimally, enough to rent to like cover the bills and stuff. But what I'm gonna really be doing is fixing up the house. That's what I'm gonna pay for my rent there. It needs a lot of work to get done, so I'm gonna be doing a lot of work there. There's a lot of other reasons I'm leaving, guys. It's not anything to do with like students here at all. It obviously never is.
He's going to.
But no, I mean, I have a brother who's your age. He's in 11th grade now.
11th grade?